Hello friends. So when considering the mechanical behavior of materials, we need two components. To describe mechanical behavior of materials, we need two critical components. One is the mechanical condition that you impose and the response of the material. Now, one conventional way of discussing the mechanical behavior of material is by considering the macroscopic response of the material to an imposed mechanical condition. So when we talk about macroscopic response, we begin by considering a sample and we impose the desired mechanical condition to it. So usually for a straightforward understanding, we impose uniaxial tensile loading and we see what is the response of this offered by the sample to the imposed uniaxial tensile loading, and this response we treat it in the macroscopic scale, meaning we see the change in the length of the sample in response to the load that we impose, and we attempt to discuss the mechanical behavior in terms of this response to the imposed mechanical condition. Now, an elegant way of depicting this mechanical behavior is by considering the response, or it's a graphical representation that includes the response along the x-axis and the condition that we impose along the y-axis. Now, when we do that, we end up being able to represent the mechanical behavior that is offered by a category of materials. So when you consider metals and alloys, the mechanical behavior of metals and alloys can be schematically represented using this graphical illustration, where you have the response along the x-axis and the load that we impose, the mechanical condition that we impose along the y-axis. So considering that all the individual metals and alloys, they tend to behave in a specific manner. They adhere to a specific form of a curve when we plot the behavior in this axis. So when you consider the axis of the mechanical condition and their responses, so load and elongation, or the strain and stress, since the category of materials, that is metals and alloys, since they tend to behave in a specific manner, so there is a characteristic way, albeit schematically, we can represent their behavior in these plots. So we saw that it includes a linear section, a non-linear section. The non-linear section will be it could be progressively increasing or it could also be progressively decreasing. Now, all these discussion, it stems from the macroscopic view of the response. We impose a mechanical condition, we look into the macroscopic response, meaning when we say macroscopic, a perceivable response by that is offered by the sample. Perceivable meaning we are able to see, after imposing the tensile loading, we are able to see the change in the dimension, the longitudinal dimension in particular, we are able to measure it. So all these we refer to as the macroscopic response offered by the material to the imposed mechanical condition, and we are able to elegantly present it in the form of a curve, and this curve, there is a schematic that we can extract from this curve that represents the behavior of metals and alloys. Now, there is also another way of looking into the mechanical behavior of the material. Of course, here the mechanical condition that we impose remains the same. So we can stick with the uniaxial tensile loading that we are imposing into the material. Now, what varies is we are now looking from an atomistic perspective. We are narrowing down, or rather we are getting down the length scale, and from the macroscopic scale we are directly jumping onto the atomistic perspective, and we want to see how in response to the tensile loading the atoms behave, and from that we want to relate it to the macroscopic behavior of the material. So what essentially we are doing is we are attempting to have a bottom-up view, starting from the behavior of material, the mechanical behavior of the atoms that constitute a material. Starting from that point, we want to relate it to the macroscopic behavior that we see while performing a study like this. So the study that we are performing is imposing a tensile load onto the material, onto a given sample, and we are studying its response. Now, in order to understand that response, we are getting into the atomistic scale, and we are seeing how the atoms behave when we see an elongation like this, and we want to relate it to the properties of the material that we observe in the macroscopic scale, and that property that we are interested is the Young's modulus. So essentially we want to arrive at an understanding of the Young's modulus of a given metal or an alloy from an atomistic perspective. By studying the behavior of the atoms and how it responds to a given mechanical condition, we want to understand how we can relate it to the Young's modulus that we see on the macroscopic scale, the Young's modulus that we are able to identify in the plot like this. So the Young's modulus is nothing but the slope of the linear region of the schematic curve that we observe when we present the mechanical behavior of metals and alloys in these plots. Now, one approximation that we can make, owing to our restriction, our focus on the metals and alloys, is that we can consider the interaction between two atoms, and these two atoms can be identical. So when you consider metals, they are made up of atoms of identical kinds, and even when you consider alloys, most of the alloys, they predominantly comprises of a base metal, meaning that base metal form the matrix in the crystal structures, and all the alloying elements replace this base metal, and therefore we have quite a higher portion of identical atoms. So therefore we can begin our discussion on the atomistic perspective of the mechanical behavior of atom by considering two identical atoms, and the interaction between these two identical atoms is primarily due to the interaction between the subatomic particles, electrons and protons primarily. Of course you have neutrons, but these two are the charged particles, and the interaction is largely because of the charges associated with this particle. Now, the interaction energy can be quantified as the product of the charges, and they are inversely proportional to the distance separating them. So the product of the charges and the distance separating them, using these parameters we will be able to quantify the interaction energy. Now the like charges that attract each other, they have a positive interaction energy. So when you consider the like charges and substitute their values for Q1 and Q2, even if this interaction is between electrons and electrons, the negative charges cancel out each other. So ultimately this interaction energy is positive in nature for the like charges. So the like charges, they repel each other, so you end up having a curve of this form. So this curve here indicates the repulsive interaction energy between the like charges. So as you decrease the distance between these charged particles, the interaction energy keeps on increasing, but as the distance between them becomes much closer, it becomes close to zero, it shoots up to infinity. Now the same goes for the interaction between the unlike charges. However, since they are unlike in nature, they have, or the curve that represents this interaction energy, they will be a part of the quadrant wherein we have negative interaction energy that is involved. So therefore the corresponding curve will be of this trend, and it is found in this quadrant. The trend for both these curves are identical because it is the product of the corresponding charges, and it has the same relation with respect to that of the distance separating them. The only difference is in the positive quadrants you have the repulsive force, the interaction between the like charges. In the negative quadrant you have the attractive force, the interaction between the unlike charges. Now the combination of these two, since the atom comprises of both like and unlike charges, the combination of both these is what yields the interaction between the two atoms. So we are not interested in the interaction between the subatomic particles, but we are interested in the interaction between the atoms as a whole. So therefore the resultant of these two is what renders the interaction energy between the two atoms. So when we plot that, so from these two we will be able to plot the interaction energy between the two atoms. So we combine these two, and that gives us the interaction energy for these two atoms. Now the unsymmetric nature of this curve is primarily because the attractive force is a long range force, it is predominant in the long range. The repulsive force is a short range force, so when you get closer and closer, when the atoms get closer and closer, the dominant role is played by the repulsive force, and therefore you have a characteristic trend to the interaction energy of the atoms. So this curve here represents the interaction energy of the atoms, and this is dependent on the distance between the atoms. So this is the distance between the atom. So the interaction energy is dependent on the distance between the atom. So therefore this energy is referred to as the interaction potential, because it is dependent on the position of the atom. So this energy is referred to as the interaction potential, and again this is between the two atoms. It is also referred to as the interatomic potential. Now there is a specific distance, this distance here R0, wherein so when the atoms are positioned at this specific distance, the interaction energy between the atom is at its minimal most state. So that means for a stable configuration, the stable configuration which is characterized by, for an equilibrium configuration which is characterized by the minimal most energy, the atoms are separated by this distance R0. So the atoms are, when the atoms are separated by this distance R0, then in that case the atoms are in their stable position. So when you consider the arrangement of atoms in a crystalline material, when we talk about the bond length, it is dependent on the R0. It is often equal to that of the equal to R0. So the minimal most energy between the interatomic potential. So when the interatomic potential is the minimal most for a given distance, that distance translates to the interatomic length in the crystallographic arrangement. So when you see a crystallographic arrangement, that in that when you see there is a specific positions for the atom, that specific position is due to the lowest interatomic potential. So this is one relation that we can make. Secondly, there is the minimal most, we can quantify this minimal most energy. How much is this corresponding potential energy for the R0? So when we say that the atoms are in a stable state, the atoms are in their ideal position wherein the energy between the atoms are the lowest. So that lowest energy can be quantified. So this energy, this lowest energy can be quantified. So this is the interaction potential at R0. So this is the lowest energy between the atoms that can be established. Now any change to the position of the atom will increase the energy. So you are moving the atoms from the stable position to an unstable position by imposing a load. So whenever you want to move the atoms from a stable position, what essentially you are doing is you are moving from the, you need to spend some energy to move the atoms from a stable position. So whenever you are imposing any force and that force changes the position of the atoms, then this is what the energy is expended for. You are expending the energy to shift the atom from its stable position, from its low energy state to an high energy state. So when you are imposing a tensile load, what essentially you are doing is you are shifting the atoms from R0 and you are increasing the length between them. So it means that the interaction potential is increasing as you impose the tensile load. And within a certain range, we are now focusing on the linear region here. So in this linear region, now when you release, when you unload your sample, now the atoms get back to its original lowest energy state. So that is what we observe in the elastic behavior. So for a given arrangement of the atoms, there is a minimal energy state, and that minimal energy state is dependent on the position of the atoms, and this R0 that ensures the minimal energy state translates to the bond length. And now when you are imposing, so you have two of the atoms. In this sample here you have two atoms A and B that are separated by R0, and now when you are imposing the tensile loading, what essentially you are doing is you are increasing the distance between the A and B atoms. So you are increasing, you are adding to the distance R0, and when you do that, you are increasing the energy, the interaction energy between the atoms, and that is the reason why when you release the tensile load, what essentially happens is the atom gets back to its original state of R0. So in order to minimize the interaction energy, the interatomic potential, the atoms get back to its original state when you are in the elastic region. So this is one extrapolation that we can make from the atomistic perspective to what we observe in the macroscopic world. So in the macroscopic world, within the elastic region, you impose a tensile load, you release it, that the system get back to its original shape. The sample, the cylindrical sample that we have, once you impose the load, it extends its longitudinal dimension, and once you release it, it gets back to its original shape. That is primarily because you are playing with the interatomic space, you are playing with the bond length, you are attempting to increase the bond length and the distance separating the two atoms, and when you do that, you are increasing the interatomic potential, and when you release it, that system wants to go back to its stable state, it wants to reduce the interatomic potential, it goes back to this energy here, and then ultimately it corresponds to its original state. Now the other relation that we can make from the interatomic potential is that depending on how low your interatomic potential is for the stable configuration, you have to, so this interatomic potential acts as the resistance for any change in the dimension, any change in the interatomic distance. So any change in the bond length, you have to overcome this interatomic potential. So only when you are able to overcome this interatomic potential, you will be able to make changes to the bond length, albeit temporarily. So therefore, when you have two systems with two metals, so to speak, with two different interatomic potentials, then the one with the lowest potential will offer greater resistance to elastic deformation when compared to the one with relatively higher interatomic potential. So one with the lowest interatomic potential will demand more tensile load to shift the positions of the atoms when compared to one with higher interatomic potential. So these are the ways we can relate our understanding based on from the atomistic perspective to the macroscopic scale. We are able to relate the R0 to the bond length. We are able to relate the elastic behavior to the shift in the interatomic potential when you change the R0. And finally, we are able to relate the interatomic potential to, qualitatively at least, to the load that is required to bring about the elastic deformation. When you have a lowest interatomic potential, when a material has a lowest interatomic potential, you have to sufficiently overcome it in order to bring about an elastic change. When it is quite higher, then you need relatively lower load to bring about a shift in the atomic positions. Now, what we have so far been considering is we have been able to arrive, or we have been able to quantify the energy associated with two atoms, the energy associated with the atoms when they are positioned in a specific manner. So depending on the distance separating the atom, we are in a position to quantify the energy established between these atoms. Now, when you talk about, or when you consider the internal energy of a system, so the system could be a metal, a crystalline arrangement of the atoms. So when you consider such arrangement of the atoms and you want to quantify the internal energy of the system, when there is no other further input that goes into the system, then the internal energy of the entire system will depend on the interatomic potential alone. So what we want to do is, we have now looked into the individual atoms, we have now compared two atoms, we have now taken two atoms into consideration, and we have now derived, or we have now at least expressed what would be the interaction energy between these atoms. Now let us take a system of metal that comprises of several such atoms, and now when we want to quantify what is the internal energy associated with the system. So the thermal effect and all the other effects are minimal to that system, so all the internal energy stems from the interaction between the atoms alone. So in that case, the internal energy of the system is completely governed by, the internal energy of the system is completely governed by the interatomic potential. So depending on the interaction between the atoms, so whatever the interaction between the atoms are, so this interaction, it ultimately translates to the overall internal energy of the system. So now what we have is, instead of considering just the two atoms, we are extrapolating, we are considering the system as a whole, and this, since in this system the thermal effect is minimal and all the effects are minimal, the overall internal energy of the system is because of the interaction between the atoms. So that means the energy of the system is equivalent to the interaction energy of the atoms that constitute the system. So you have a system comprising of several atoms. So these atoms, let us assume they are regularly arranged as we find in a crystalline metals, and there is interaction between each and every individual atoms, and there is no other contribution. So the overall energy of the system is then nothing but the sum of all the interaction energy. So that is what we mean when we say, what we mean by this expression, that is the internal energy of a given system is primarily governed by the interaction energy, because we have assumed that there is no thermal effects or any other effect associated with it. Now in that case, when we are imposing a uniaxial tensile loading, so we have a system, the internal energy of the system is entirely based on the interaction or interatomic energy, so interatomic potential energy. So in that case, we are, for such a system, we are imposing a uniaxial tensile loading. So what happens is, we are doing some work on the system. So you are imposing a uniaxial tensile loading, you are doing some work on the system. So this consequently changes the internal energy of the system. So we have introduced the internal energy, we have related the internal energy to the interatomic potential which we have seen. Now we are imposing a uniaxial tensile loading. As a consequence to this uniaxial tensile loading, there is a change in the internal energy. So this change in the internal energy in response to the uniaxial tensile loading that we have imposed, according to the first law of thermodynamics, which I believe you would have come across in your previous semesters, can be expressed as this. So what essentially we are doing is we are just rewriting the first law of thermodynamics. Here if this term involves the heat transfer that is associated with the system, it can be in or out of the system, and the W is the work. Now our assumption is whatever heat transfer or whatever role that heat thermal energy plays in the system is minimal. So therefore this term is rather insignificant. There is no role played by this term here. So ultimately the internal energy change is principally governed by the work that is done on the system, and this work is nothing but the work. When we say work, what we are essentially doing is we are imposing a uniaxial tensile load. So the load is nothing but the force. So the uniaxial tensile load that we impose is nothing but the force that we impose onto the system. In response to the force, there is a displacement in the positions of the atom. So R is the position of the atom, the original position of the atom. So in response to the force that we impose, there is a change in the position of the atoms. So the work that we do on the system can be quantified as the product of the force and the change in the interatomic distances. So we start talking about the internal energy of the system based on the interatomic potential energy. And now what we essentially do is we bring about or we impose a uniaxial tensile load, and when we impose a uniaxial tensile load, there is a corresponding change in the internal energy, and in order to quantify the change in the internal energy, we bring the first law of thermodynamics into play. And the first law of thermodynamics, we assume that the role of thermal energy is zero. So the first law of thermodynamics, it reduces to this expression here. Now when we want to quantify the work that we do, so the work involves we impose a uniaxial tensile force, and so this force brings about a change, and work is nothing but the product of force and distance. So we impose a force, that is the uniaxial tensile load, and there is a change in the displacement, that is there is a displacement that is introduced, that is the change in the position of the atom. So we combine these two, and now we have an expression for the work that brings about the change in the internal energy. So essentially what we have is we have a change in the internal energy. Since the change in the internal energy is quite small, we can express it as in this way, and this corresponds to the change in the internal energy because we have considered a system wherein the internal energy is equivalent to the interatomic potential energy. We express this, which can be expressed as the change in the interatomic potential energy. This is equal to, from this expression here, this is equal to negative of the work done. So whatever change is being brought about by the change in the internal energy. So how we bring about the change in the internal energy is by imposing a uniaxial tensile loading. So therefore it is the product of force and displacement. So ultimately the expression that we have is the change in the interatomic potential when you impose a uniaxial force is this way. So we can express the change in the interatomic potential when you impose a force onto the system can be expressed in this manner. So ultimately what this expression yields is that when we want to quantify, instead of considering the interatomic potential energy, when we want to consider the interatomic force, this interatomic force is nothing but minus change in the interatomic energy with respect to the distance separating the atoms. So we began with a system. The system comprises of atoms, and based on the interaction between the atoms, we quantified the internal energy of the system, and we impose a force, and that force changes the internal energy of the system. So we want to quantify the change in the internal energy of the system based on the force that we have imposed, and that expression is given here. So essentially we have quantified the change in the internal energy of the system with respect to the force that we have imposed. The force that we are talking about is the uniaxial tensile loading. Now this internal energy is dependent, it's solely governed by the interatomic potential. So when we are saying that the internal energy of the system changes, what we are saying is there is a corresponding change in the interatomic potential. So therefore we have related the change in the interatomic potential energy to that of the force that we have imposed. So we are relating two scales, change in the interatomic potential, the atomistic scale, and we are talking and we are expressing it in terms of the force, that is how the force changes this interatomic potential. Now we want to have an expression for the force, and that force is given, or we can, from this expression here, we can derive a relation for the force. Now using this, we will be able to quantify the interatomic force. So what we have here is a term that quantifies or that expresses the interatomic potential energy. So the change in the interatomic potential energy with respect to the distance between the atom gives us the interatomic force. So we already have seen how we can graphically represent the change in the interatomic potential. The change in the interatomic potential with respect to the distance separating the atoms, it adopts the form like this. So this we were able to understand. Now this is the interatomic potential energy. So starting from this, we want to understand what is the corresponding interatomic force. So from this depiction here, we want to understand using this relation. So we have a depiction here indicating the interatomic potential energy. From this depiction here, using this relation, we want to find out the interatomic force. So what is the interatomic force that is involved? The reason we want to focus on the interatomic force is because once we are able to establish the relation between the interatomic force and the distance separating the atom, we will be able to establish the relation for the load that we impose macroscopically. Let me repeat, when we are able to arrive at an expression for the interatomic force from the interatomic potential energy, so you have an expression for the force that is acting between the atoms, and on the macroscopic level it is the force that we are imposing on the material. So once we are able to arrive at an expression for the force in the atomistic scale and we have an understanding of force in the macroscopic scale, then relating these two will become rather straightforward. So for that reason alone, we have done all these numerical gymnastics and we have arrived at this expression here. Now this expression should help us arrive at a curve that represents the interatomic force as the R changes. So what this expression here indicates is the slope of the curve, how the slope varies with respect to R is nothing but the interatomic force. So what this expression means is, in the conceptual term, the slope of this curve is nothing but the interatomic force. So this slope of the curve is varying with respect to R. So if we are able to gather the trend that is associated with the change in the slope of the curve with respect to R, then we are ideally able to schematically represent the interatomic force. So when we want to represent the interatomic force which is dependent on R, all we need to do is we need to understand how the slope here changes. So when we are able to understand how the slope here changes, we will be able to have a schematic representation of the interatomic force. Now in this case, what we have is in this region, so let us split the overall curve here indicating the interatomic potential into different sections. So here it is the minimal most point. So this is the minimal most point. So at this point the slope is 0, and here what we are considering is the slope of the curve. So the slope of the interatomic potential energy is the slope of this curve here is the interatomic force. So at this point, that is R0, the slope of the curve is 0. So at the same point R0, when we say the slope of the curve is 0, it means the force, interatomic force, is 0. So at this point, we have one point wherein the slope is 0, the same point we have arrived at here. So this is 0. Now, in this section, what we have is, we have a negative slope, and this negative slope is decreasing. So we have a decreasing negative slope in this section. Between this and this, we have a negative slope that is decreasing. And since what we are considering for illustrating the force is the negative of the slope of this curve, that means we have a decreasing slope in the positive quadrant. Let me repeat, in this section between this and this, we have a negative slope that is decreasing. So in this section, we have a negative slope that is decreasing. In order to understand the force from this section, we need to take the negative of it, and then we need to consider the slope. So negative slope that is decreasing, so we will have a decreasing curve here, but we will have it in the positive quadrant because there is a negative sign already associated with it. So this section here in the force curve will adopt a form like this. So let me use red. So we'll adopt a form like this. So we have now expressed this section here. Now, in order to express this section, as you can see, so there is a change in the slope. The slope is gradually decreasing, and beyond the point it remains constant. So it is till this point there is a point of inflection. So there is a point of inflection. Till that point, the slope is increasing. So you have a positive slope that is increasing, and beyond the point of inflection, it begins to decrease and assume a value that is constant. So this section of the curves has two parts. In the first part, there is an increasing slope, and beyond this point, the crossed out point, there is a decrease in slope, and this is called as point of inflection. So the point of inflection means there is a significant change in the direction of the slope. So there is a point of inflection, and in this point of inflection there is a change in the direction of the slope, and therefore when you plot it, you end up with a curve like this. So this is what the point of inflection is. So till this point here there is an increasing slope, and beyond this point there is a decreasing slope, and since we have a negative sign associated with it, there is a reversal in the sign. So ultimately what we have now arrived at is, we have now arrived at a schematic representation of how the interatomic forces, it varies when you it varies with respect to length. So essentially what we have considered is, we have considered just the distance between the particles, and what we have seen is, when we plot the force or interatomic force and how it varies with the distance separating the atoms, the distance separating the particles, then essentially what we end up having is, we end up having a curve that reflects the negative slope of the potential energy curve. So based on the potential energy curve, the interatomic potential, by considering the negative slope of it, we have now arrived at a schematic representation that indicates how the force between the two atoms vary. How the force between the two atoms vary is what we have arrived at now. So at the point R naught, so let us go back to our initial R naught case. At the point R naught, the force, the resultant force between the interatomic potential interaction, so we have an interaction, and the resultant force at R naught is equal to 0. So we don't have any force between the two atoms when it is in its stable state. When it is in the equilibrium state, there is no force associated with it. So only when it moves away from the state, there is a force that is associated with the atoms, and this force, it results in allowing the atoms go back to its original state. Let me repeat, when the atoms are in the stable state, when the atoms A and atom B are separated by the distance R naught, the force between these two are 0. Now when you impose a uniaxial tensile loading and you shift the R naught, say you shift the A atom here, thereby increasing the value of R. So you now have a new distance separating the atom A and B. For the case R, for the distance R, you will have a non-zero force that is acting between A and B. And now when you remove the load that brings about this change in the distance separating the two atoms, what you end up having is this non-zero force allows for the atoms to get back to their original state. So when you have two atoms separated by R0, the force between those two atoms is 0. When you separate these two atoms, you are introducing or you are establishing a force between these atoms. So externally you are imposing a load, and this load separates the two atoms, and this load brings about a force within the atoms. So there is an interaction force within the atoms, and once you remove the external load, in order to neutralize this force that has been established, the atoms go back to their original state, and this is how the elastic behavior is observed. So we saw the elastic behavior in terms of the interatomic potential energy. That is, the interatomic potential energy, it varies, it increases, and in order to reduce this energy, the atoms go back to their original state. So this is one understanding that we gained from this plot here. So from this plot here, we gained that understanding. Now what this plot indicates is, it helps us understand how the force that we impose translates the positions of the atoms. So there is a load that we impose, it translates the positions of the atom, and when the position of the atom is changed or it varied from R0, there is an interatomic force that is introduced. And now when you remove the load, this interatomic force, it is responsible for the atom is getting back to their original position. So now when we consider the stress strain curve, or let's say load elongation curve, what we are essentially considering is, when we consider the load and the elongation curve, what essentially we are considering is the force and the change in the position of the atom. So force and the change in the position of the atom. So what essentially we have is, we have the load elongation curve. When you consider this load elongation curve in the atomistic scale, what you end up having is this force and the curve and the force and interatomic distance curve. So on the macroscopic scale, it is load elongation. In the atomistic scale, it is the force versus the interatomic distance curve, and that is exactly what we have here. So the curve that we observe here is similar to that of the load elongation curve. So in load elongation curve, on the one axis you have the force, on the other axis you have the elongation. In the same way, in this curve we have the interatomic force and we have the distance that is separating the atoms along the x-axis and the interatomic force along the y-axis. Now in the elastic region, the Young's modulus E is nothing but the slope of this line here. So in the elastic region, when you consider the macroscopic representation involving load and elongation in the elastic region, the Young's modulus is nothing but the slope of the curve here. In the same way, since we have already established that the load elongation curve, so here it is the stress in the strain curve, in the stress and the strain curve, what we essentially have is the slope of the curve is nothing but the Young's modulus. So the Young's modulus, the trend of the curve remains the same irrespective of it is represented by load or elongation or the stress and strain. Irrespective of the parameters that we use to describe the mechanical behavior of the material, the trend remains the same. So therefore, for load, elongation and also for stress and strain, the elastic region remains the same, it remains linear. And when you consider the slope of this linear region, what we end up having is the Young's modulus. So similarly here we have a similar representation involving the force and the distance separating it, and this trend will remain the same even if you replace this force through appropriate manipulation, even if you replace it with stress, and even if you replace this with strain by dividing it by the suitable constant, this trend is now going to remain the same. Now when the trend remains the same, the slope of the curve should then indicate, or it should then reflect the Young's modulus. So similar to this curve here, the slope of this curve should also indicate the Young's modulus, because similar to this curve which has the stress along the y-axis and the strain along the x-axis, it is possible for us to relate the same parameters to the interatomic force and the distance separating it. So therefore, the slope of the curve particularly around R0. So R0 is the stable configuration. So R0 is the configuration of our sample. So when you focus on the R0, when you consider the R0, the stable configuration, the slope of this curve around R0, the slope of the curve around the R0, the stable configuration, will give you the Young's modulus. So that means the slope of the curve can be expressed in this way. So this is what gives us the Young's modulus from the interatomic forces. So to give a quick review, what we have seen is we were able to arrive at an expression that relates interatomic force to the interatomic potential, and this relation indicates that the interatomic force is the negative of the slope of the interatomic potential, how the interatomic potential curves varies with the distance separating the atoms. Now with that understanding, we were able to graphically illustrate how the interatomic force varies with the distance separating the atoms. So based on this expression here, we were able to illustrate graphically how the interatomic force varies with the distance separating the atoms. So what we essentially have in this representation is the force along the y-axis and the distance along the x-axis. Now because of this characteristic description of the plot, we are able to relate it to the load elongation curve, because in the load elongation plots also we have the force along the y-axis, because load is nothing but the force. We have the force along the y-axis and the elongation, which is nothing but the distance variable, along the x-axis. So along the x-axis you have elongation, a distance variable, and along the y-axis you have the force, which is similar what we observe in this representation here. So here it is force versus the distance, and also here when you consider the load, this is also force versus the distance. Now we saw that it is possible for us to also conceive that when we take the ratio of these different parameters with respect to the constant, the trend is going to remain the same. So therefore, even when we consider the stress strain variant of this curve, the trend is now going to remain the same. And when you consider the slope of the curve is what yields us the Young's modulus. So the slope of this curve yields us the Young's modulus. Now in the same way, it is possible for us to have a similar trend when we replace the corresponding variables, but in this case, even if we leave it as it is, because in this case we are dealing at the atomistic scale, and in the atomistic scale we don't have the original cross section area similar to the ones that we have in the macroscopic scale. So therefore we can leave this representation as it is. And now when you consider the slope of the curve, because here the slope of the curve gives you the Young's modulus, in the same way when you consider the slope of this curve here, particularly around the stable state, because in the macroscopic scale we are considering the stable sample. So in the same way when we are considering a sample, it means the interatomic distance are in a stable state. Before we impose the load, the interatomic distance are in the stable state. So when you start from this point and when you measure the slope of the curve, what we end up having is the Young's modulus. So what essentially we have done is we have considered the behavior of a material in the atomistic scale, and we were able to relate the different behavior of the material in the atomistic scale to what we observe in the macroscopic level. In addition to why the material gets back to its original state and how much load we impose on a given material to bring about an elastic change, in addition to all these, it is also possible for us to quantify the Young's modulus from the atomistic perspective. So there are conceptual relations that we can make from understanding the mechanical behavior from the atomistic scale to that of the macroscopic scale. So these conceptual understanding includes, we are able to state why a given extent, so when you extend or when you impose an uniaxial tensile loading and there is a longitudinal increase in the dimension, why it goes back to its original state, it can be explained by both the interatomic potential and also interatomic force. And besides that, it is also possible for us to say it that when we are comparing two different metals, one has the lower interatomic potential, the lowest interatomic potential in the stable state when compared to the other, the one with the lowest interatomic potential will demand more load to bring about an elastic deformation when compared to the other with the higher interatomic potential. Even that understanding can be gained from the discussion from the atomistic perspective. Besides all this, this expression here helps us to quantify the Young's modulus, one characteristic property of a material in the elastic, during the elastic deformation, in the elastic regime of the mechanical behavior. The characteristic property of the material is Young's modulus. This Young's modulus can be calculated from the atomistic perspective. So the atomistic perspective gives us an explanation of the elastic behavior, why a metal should go back to its original state when it is deformed. In addition to that, it also helps us quantify one of the critical parameters that prescribes the elastic behavior of the metal. So again, we need to qualify this expression here because this slope is not anywhere, but this slope is around R0. So the more accurate way of writing this expression is the Young's modulus is nothing but the slope of the interatomic force curve when expressed with respect to the distance between the atoms at the stable state. So Young's modulus is nothing but the slope of the interatomic force curve when plotted with respect to that of the distance separating the atoms at the stable state. You are plotting the interatomic potential, so you are plotting the interatomic force with respect to the distance separating the atoms. The slope of this interatomic force, at the stable state will help us quantify, will help us measure, or from that we will be able to estimate the Young's modulus. Now, the reason this understanding is quite important is because if we are doing some atomistic simulation, if you are doing some molecular dynamics study, and all that we are studying is how the atoms behave with one another, or how the atoms interact with one another. If you are considering a crystalline system based on the interaction between the atoms alone, so supposing you are working on a problem and you are considering developing a new material and you are considering developing a new alloy, and now this alloy you are able to do it in a simulation domain, you are able to build this alloy in an atomistic scale, and you want to know what could be the Young's modulus of this alloy. So you want to know how well, or you want to build a given alloy with a given Young's modulus, and you want to know what could be the alloy composition that would give me this Young's modulus. So you can have, when you consider a system like that, and you can play around with the different combination, different alloy combination, you can bring about different combinations of atoms, you can bring about different combinations or different interactions between the atoms. Now that you have an expression that relates the interatomic interaction, interatomic forces to the Young's modulus, you can create such a configuration that brings about the desired Young's modulus. So from working on the atomistic range, this expression allows you to quantify a parameter that is often associated with the macroscopic observation. So when you are working on an atomistic simulation, when you are considering the molecular dynamics, when you are considering the interaction between the atoms alone, from that you will be able to estimate a macroscopic property like Young's modulus. In addition to that, when you want to have, so you have a fixed Young's modulus that you need to achieve. Now this fixed Young's modulus, you need to achieve it by appropriately changing the atomic arrangement. So this expression allows you to bring about the right combination of atomic interaction, interatomic interaction and interatomic forces. So this expression allows you to bring that right combination of atoms that gives you the required interatomic potential, interatomic forces that will ultimately yield the desired Young's modulus. So that is the reason we need to establish this bottom-up approach of relating the interatomic interactions with the macroscopic properties like Young's modulus that we observe. So this relation helps you to build a setup that will give you, in the atomistic scale, it will help you build a setup that will give you ultimately the desired properties. So in the upcoming sessions, we will see what other properties, or not particularly from the atomistic view, but what other responses are offered by the material in the macroscopic scale. Goodbye.